Okay. So we can use the derivative to find the tangent line over here. And we said that the slope of this line m was equal to f prime of x. So now in multivariable calculus, we would like to be able to do something similar, but now just with planes. So here's our surface. And here's, let's say, a point. And we would like to find a plane that is tangent to the surface at that point. Let's say this plane over here. And we can use this plane for a couple of things. We can use it to approximate the surface linearly, which means we can take small steps down here. Let's say that this point over here is the point AB, and we can move over here. So that would be, let's say, A and B plus H. And instead of plugging this point into the surface, we can plug it into the plane. So that would be somewhere here, and it would approximate the solution. We could approximate the solution by just plugging it into the plane. So that would be a benefit, kind of similar to lines. Instead of looking at this point over here, which would be the point A, and that would mean that this line over here would be y, or let's say f of x minus the y coordinates. So let's say y0 not f of x, the line, let's say g of x, is going to be equal to m of x minus x0. And that would be this line. And so then we can say that the line is going to be equal to mx minus mx0 plus y0. And that would be the line, and then we can approximate f of x by g of x. So g of x is approximately f of x around the point x0, y0. So here would be our x0, and here's our y0. And so they approximate each other. So similarly, and then let's say g of x0 plus h. So let's say this point over here, that would be that point over there. It's approximately f of x0 plus h. Any questions about this so far? Okay, so same thing we can do with 3 dimensions. And they're saying that first we can think about having 2 lines that are tangent to the this surface, and these 2 lines have the slope f of x and f of y respectively, like we said last time. So if here's our plane, we can think about and we want to find the tangent line at some point. So here's the point, and it's the point AB. So we can think about this line, we can think about this line, and then we can have 2 tangent lines to the surface. At this point, we have this line, which is tangent, and that line, which is tangent. And the slope of this line, m, is equal to f, 1 second, so this is going to vary with respect to y, so f of y. And the slope of the other line, so now that's varying with respect to x, so that would be m is equal to f of x. Now, once we have this, we can think about two vectors, or we can think about the two vectors f of y and f of x. So that would be, let's say, one vector would be this, and a second vector would be this. So this, let's say, is the vector 0 for x. It's not changing in the x direction. Sorry, so 1 second. No, this would be f of x. It is changing in the x direction, 0 in the y direction. And then in the z direction, we can say that that is going to be, sorry, 1 second. Okay, so they're doing it a little differently. They're saying that we can write this as 1, 0, f with respect to x, and this vector would be the vector 0, 1, f with respect to y. What it means is that as we take one step in the so for this one, as we take one step in the x direction, we're taking an f of x step in the z direction. And over here, this would mean as we take one step in the y direction, we take an f of y step in the z direction. That just tells you how, because we know that f with respect to y is equal the change in z over the change in y. And if you take one step in the y direction, it will tell you what your change in the z direction is going to be. Okay, so now once you have these two vectors, we would like to find a normal vector over here. And once we do that, we can find the tangent plane. So we would have these two vectors. We would take their cross product. So that would be I, j, k, and then 1, 0, f with respect to x, 0, 1, f with respect to y. And this would give us the vector that is orthogonal or normal to the surface. And so then this is going to be equal to I, and then this times that, minus that times that. So that would be minus f of x minus j f of y plus k times 1, which would give us the vector negative f with respect to x, negative f with respect to y, and 1. Okay, so now we just need to dot it with this point in order to get our tangent plane. And that point would be the point, let's do in general, x, y, z. So that means that we will get negative f of x with respect to x times, let's do this x0, y0, and z0. Okay, times x minus x0 minus f with respect to y times y minus y0 plus z is equal to 0. Okay, so then we would have, let's take z to the other side and get rid of these negatives. So we would have f with respect to x times x minus f with respect to x times x0. Let me actually not distribute. So that would be f with respect to x times x minus x0 plus f with respect to y times y minus y0 is equal to z. And this is the formula for the tangent plane. So Similarly, yeah, they take this cross product. They're using a and b instead of x0 and y0, but it doesn't really matter. And so then they get to the plane, and they say that our plane is going to be, oh, sorry, and there's also a z minus z0 over here. So this would be minus z0, and z0, of course, is equal to f of x0, y0. So that would get us f with respect to x minus x0, plus s with respect to y minus y0, plus f x0, y0 is equal to z. Okay. So again, that's this formula over here. Z is equal to f of AB plus fx AB x minus a plus f with respect to y AB y minus b. So instead of x0 and y0, if you're looking at the point AB at the bottom, you would get this. So that would be fx AB x minus a plus fy AB y minus b plus f of AB that is equal to z. Okay, any questions about this so far?
Yeah, Professor, I don't know why that's equivalent to each other. Like from x minus x0, you get it into a comma b times x minus a.
Oh, so it's just take x0, y0, and z0 to be equal to, and just x0 right now would just be a. That's just what they're using. Instead of x0, they're using the point a, and y0 would be b, and z0 over here would be f of ab. So it's just the difference between calling this point down here AB and this point over here f of AB, or just x0, y0, and z0, calling this point x0, y0, and z0. Okay, did that help?
Yeah, but where do you get the x minus a? I
Oh,
mean,
so once you have the x0 is a, you would just substitute this x0 and put an a. And this is also, so let me take this and move it down here. If you write this out more completely, you would get f of x, x0, y0, x minus x0, plus f of y, x0, y0, y minus y0, plus f of x0, y0 is going to be equal to z. That's if you write it out. And then you just say, okay, so in our case, this is going to be a, this is going to be b, this is going to be a, this is going to be a, this is going to be b, b, a, and b. And that you just substitute and you get this.
okay. And just another thing. So you did cross product because that's the normal vector of the plane. Is that correct?
Yeah, so here's the cross product of these two vectors, that vector and that vector, and you get the black vector, which is the normal vector to the surface or to the plane. It's going to be the normal vector of your plane. So then you just use the formula that we have, right? So we had that normal vector, the plane would be the normal vector dotted with x minus x0, y minus y0, and z minus z0 is equal to 0. That's the most general formula for the equation of a plane. assuming that you know the normal vector. So we know the normal vector. The normal vector is the vector negative f with respect to x, negative f with respect to y, and z. And that we dot with x minus x0, y minus y0, and z minus z0. And we say that that's equal to 0. Okay? Did that help?
Yeah, thank you.
Okay. Let me start on the page. Okay, so like I said, we can then use this to find a linear approximation of the plane, which would just be this, if the surface, which would just be this plane. The linearization would be the equation of the plane at that point, and that would linearize f of x at AB. And as they say, the linearization can be used to approximate f of x near AB, which for us again is x0, y0. I'm going to try to stick to AB from here on so that it just fits with the book. The graph L of x, y is the plane, this plane over here, determined by f of x and y of f of y the way we just saw, finding the normal derivative, the normal vector, and so on and so forth. Okay, and then I'm going to basically ignore the rest. Okay. So let's try to do an example, body of mass index. So they're telling us that a person's BMI is I is equal to W over H squared. So let me just write some of this. I is equal to W times H squared. Divided. Okay. Where W is the body weight and H is the body height. Estimate the change in the child's BMI if WH changes from 40, 1.45, so 40, 1.45, changes to 41.5, 41.5, and 1.47, and 1.47. Okay, so the easiest way to do this is to again create a tangent plane to our surface, and then plug in this point into our tangent plane. See what the answer is. Plug it this point. If we could plug this point into here and plug this point into here without a calculator and figure out what that is, then we would be done. The problem is this H squared and the 1.47, I wouldn't know what that would get you. And the W over that, it would be even more complicated. So if I don't really have a calculator and I want to basically figure out what happened over here, I can plug this in, see what number I get, plug that in, see into my linear approximation, and that will tell me the difference between these 2 points, or how much Z has changed from this point to that point. So in order to do that, we're going to use the formula Z is equal to f of 40, 1.45 plus f with respect to x. Let me try to, okay. Yeah, f with respect to x of 1 second. 40, 1.45 times, and then we're going to have x minus x minus 1 second. So they're gonna, yeah, so that would be the difference. Okay, I would just do x minus k. 40. That would be the x coordinate, and then f with respect to y at 40, comma 1.45 times x minus 1.45. Now notice if, oh, sorry, y. Okay. Now notice if I find this, the f of x, the y of x, and then I plug in my 40 and my 1.45 into the x and into the y. I plug in 40 into the x, so this disappears. I plug in 1.45 into the y, so this disappears. I'm only left with this, which makes sense. If I try to figure out exactly what this is going to be at 41.45, I'm just going to be left with this over here. But if I now plug in this point over here and this point over here, I am going to get, or this will give me the new approximation or difference between the 2 points. So it'll be this plus something, and this will be the extra something. So I can actually ignore this for this problem, and I'm going to ignore this too. I really only need to figure out what this over here is, and that will give me the difference plugging in x, for x plugging in 41.5, and for y plugging in 1.47, and that will tell me what I want to know, which is the difference between this point and that point. And any questions about that? Okay, so the so let's look at the partial of I with respect to W. And that would be over here. So let's actually rewrite some stuff. So this should be F of WH. And so then over here, I would say instead of having X, we will have, let's say W. Now the question is which one is the height and which one is the weight. So WH, the first one. Good. So W, good. And then the next one is going to be F with respect to H. And then the X over here will be our W. And the Y over here will be our H. Okay. So the partial of I with respect to W, which is FW, is going to be equal to just 1 over H squared. Ooh, where was this? Oh, here. Okay, so 1 over H squared. Good. So now the partial with respect to H, that's the partial of I with respect to H, that is going to be, and we're going to take this times the derivative of that, which is nothing, and W times derivative of this, which would be W time minus W times 2H, yeah, and then H to the fourth over H to the fourth, which would give us negative 2W over H cubed. Let me see, -2. Okay, perfect. So now, we can plug in our, so now we can find f of W and f of H at those points. So f of W at the point 41.45, 40, comma 1.45. That is going to be 1 over 1.45 squared. And f, and they say that this is, and this we would only have to do once in this approximation. And then we could use this to always approximate different points that are close. But this would be 0.45. No, 48 maybe. Yeah, 0.48. Okay, now this is going to be -2 times my W, which is 40, over 1.45 cubed, and they tell us that is negative 26.42, negative 26.42. So now I can rewrite this as my change in Z, my delta Z, and this over here is going to be Z minus Z0, that's my delta Z. So that's going to be equal to F of W at this point, which is 0.45, 0.48 times delta, the change in X, plus a negative, so minus 226.42 times delta Y. That's what my delta Z is going to be, my change in Z. So now I just need to know what this is, and I need to know what this is. So that would be equal to 0.48 times, and then we would have 41.5 minus 40. So this would be 41.5 minus 40 plus minus 26.42. And then my delta Y is going to be this over here, which when I plug in my H, my new H, it's 1.47 minus 1.45. 1.47 minus 1.45. Okay, so this is going to be equal to 0.48 times 1.5 minus 26.42 times, and this would be 0.02. Yeah, so this is 0.00, okay. And so then when we do this, we get 0.2. So this is 0.2. So if I move in my W direction from 40 to 41.5, and I'm moving my H direction from 1.45 to 1.47, I approximately, in my Z direction, my delta Z is going to change by 0.2. Any questions about this?
Professor, this is just um a, a kind of stupid question, but why do we have to approximate? Why don't we just plug in into the actual equation?
So I agree that these days we have calculators, and all this linear approximation stuff, which kind of was something that Newton did, and is not really that beneficial, although it is, because it's linearization is a very, very common process if you're doing a proof in something. And then it's abstract and whatever, you're linearizing, and it simplifies the problem. So from that perspective, we need to know how to do this. But if it's in order to find these type of differences, like in terms of actual numbers, you're right, you can plug in the original point into this and the new point into this and see what the difference is. But you would have to use a calculator, because that I don't know what 41.5, plugging this into here would just be it's hard to figure out what that is. That being said, it's also far hard to figure out what these two partial derivatives are. But you only have to do that once. And then you can continue looking for new points, finding their deltas, and you will have a good approximation for what the change in I is.
I see. Thank you.
All right. Okay. So let's try a new problem, but before they tell me what the solution is, it would be good to know the problem. Is it this? No. Okay, so I'm going to skip this problem unless anyone can see where the problem starts. Okay, whatever. Oh, how is that exercise? Okay, I think there's something wrong with this chapter. Exercise 6, and then you have exercise 3. Oh, exercise and example. Sorry, 1 second. No, example 6 and example. Okay, whatever. I think there's something wrong with this chapter. And, oh, is it going backwards? Example 3. Oh, that's that again. That's not. Huh. Sorry. Okay, let's just do this last example, and I think we can stop there. I mean, at that point, everything is just formulas, and you can do homeworks in order to practice. But I'm going to do the example finding the tangent plane. This chapter, I don't know, something went wrong. But they ask us find an equation of the tangent plane to the graph of f of xy is equal to xy cubed. So f of xy is equal to xy cubed plus x squared at the point 2, -2, 2, -2, and f of 2, comma, -2. So just useful to figure out what this point actually is. So if we plug in 2 and -2 into here, we're going to end up getting negative 2 to the 4th power plus 2 squared. Okay, so that would just be, 1 second. This is going to be our f of 2 comma -2. And I'm just going to use that instead. So, okay, so they want us to find the tangent plane, and we said that the tangent plane can be written as f of 1 second, f of xy, and this would be the tangent plane. So the tangent plane is going to be equal to f of 2 comma -2. We can say that this is approximately f of 2 comma -2 plus, so this over here is our z0. This over here is our z, plus f partial of f with respect to x2 comma -2 times x minus 2 plus partial of f with respect to y, 2 comma -2 times y plus 2. So this over here, okay, this is, we know what this is, f of x, okay. This over here is my a, which is equal to 2. And this over here is my b, which is equal to -2. Okay, so we need to figure out what these partial derivatives are. So f with respect to x at 2 comma -2, that's going to be equal to y cubed plus 2x, which is going to be equal to -8 plus 4, which is going to be equal to 4. F with respect to y at 2 comma -2 is going to be x, okay, 3x y squared. That's the only thing. And then we would have 3 times 2 times 4, which is going to end up being 6 times 4. Yeah. Okay. Any questions about this so far?
Can you just write out the last answer?
Oh, yeah, 1 second. I just want to make sure that so far everything is good. -4, 25. Okay, yeah. So then the answer is going to be f of xy is going to be approximately f of 2, -2. I am going to just put that in. Plus, oh yeah, sorry, -4. Okay. -4 times x minus 2 plus 24 times y plus 2. And you can leave it like that. That's the plane. So here's our tangent plane. It's basically that to this surface, at the point 2, -2. Any questions about this? Okay, so let me just go to the summary and then we can stop here. So again, in summary, this over here is the equation of our tangent plane. Z is equal to f of AB plus f with respect to x at AB, x minus a plus f with respect to y at AB, y minus b. The linearization, same exact thing. So tangent plane linearization, basically the same thing. The approximation by linearization is just f of x is approximately that. Okay, same, all very intuitive. And then the change in of the approximation is this over here. Notice we just ignore this. We take this to equal delta x, just a notation. We take this to be delta y. So all still coming from this original equation. And that's basically that. I mean, this over here is just this, but written a little differently. df, dx, dy instead of delta x, delta y, and delta f. Okay, any questions about any of this? So let me just make sure that the next section is kind of okay, gradient. Fine, so yeah, next time we're going to continue with gradient. If there aren't any questions, then we will stop here. Okay. Okay, have a nice day.